Do you hear me? Yes, you hear me. Okay, thank you first to the organizing committee for inviting us to present our work today. It's a pleasure. Today I will talk to you about, I don't know, which is the one that's, it's the same as mine. Is there a pointer? No, it doesn't work. Mine works. Well, I try with mine. So today I will talk to you about administering bromide to treat autism. Or let's not say treat, but relieve autistic symptoms, to be really honest. So does that work? Yeah, okay. I will just give you a short introduction about where we are about pharmacotherapy in autism. So what we have for now and what works actually are cognitive and behavioral interventions in patients. And these ones, they're efficient, but they are not efficient for all patients. They have to occur quite early in development, so they would not match for adult people, for example. That would not work. They're highly demanding because you have to work between 20 and 40 hours per week with the kids to have a real improvement. And so they are quite costly, and that's not only a matter of money, but they're costly also in terms of human beings for the people and for the relatives. For the patients and their relatives. So ideally, it would be great to have some pharmacotherapy, maybe not alone, but at least as an adjunctment to the behavioral therapies. But for now, there are very few approved pharmacotherapies, treatments. Essentially, there are some atypical antipsychotics, but they don't relieve social deficits. There are specific treatments for comorbidities like sleep disorders or epilepsy, but there's nothing to relieve social deficits, which are the main trouble, maybe not the main, but the ones that is very characteristic in this pathology. So this is still French, that's funny. Okay, sorry. So at this point, usually I was showing that there was some hope for new treatments. And the ones that you may have heard about are the mGlu5 targeting therapies, with the mavoglurant, for example, or the baclofen that was targeting the GABA-A receptor, and you probably all know that they failed in clinical trials. And so at this point, usually I say, well, we have some hope because there are new trials like oxytocin or Bumetanide. And you also probably know that they failed last year. So there's nothing actually really promising for now that is under trial that would give some results. Hopefully, what we have tried in the study is more promising. So the way we work in the lab is that we have models of autism, different models that are genetic models or environmental models, the ones that you give some toxins and you have an effect on the behavior. How it works actually, how would you qualify a mouse line as a model for autism? So you have to check 3 types of criteria for validity of the model. The first one is the facial validity. So in your model, you should see similar symptoms as you would see in the patients. When I say similar, I don't say they're the same. I'm talking about mice, okay? So mice, they have a behavioral repertoire that is not human repertoire. So these guys, they will be autistic in a murine way, not in a human way, okay? And so they will show the diagnostic, the dyad that qualifies autism in the case of a model for autism, which are social deficits. I'm not sure it works actually. Social deficits and stereotypes or restricted interest or lack of flexibility that you can measure in mice. And also you can detect some comorbid signs such as anxiety or motor impairments that have triggered some attention in the last years. Then they also have to check for construct validity. Well, this is for genetic models is not a problem because actually the mutations you have in mice are usually the same or they're very similar to the ones that you would find in humans. And that's the way the models have been created initially. You can also have models with early exposure to toxics different toxins such as, you know the depakine model, the valproate model is exposure to depakine. No, sorry, the last criteria for validity is the predictive validity. And in autism, it's quite tricky because actually there is no treatment that actually relieves the social deficits. So you have no reference molecule you can compare for now that is really used in the clinics, because the idea would be if it works similarly in mice and humans, then the mouse model is a good model. Okay, so for today, I will talk about bromide, and talking about bromide, I have to talk to you about the excitation-inhibition balance in autism. Actually, nobody knows exactly what is the etiology of autism, not only the cause, but the mechanism, let's say. What are the underlying neurobiological what is the underlying neurobiological mechanism? And it has been proposed that glutamatergic transmission would be excessive in patients, and GABAergic transmission would be deficient. It's not always verified, but there is some consensus about the deficient GABAergic transmission because it's found in different types of patients, in different syndromes like Fragile X, for example, and it's also found in mouse models. It has been proposed that this problem with the balance between the inhibition excitation balance would be the result of the difficulty in neuronal maturation. So this theory is the one that has been proposed initially by Becker. And he explained that probably because during maturation of the neuron, chloride-ion gradients will develop, and I tried to explain that. And so based on the frequent comorbidity between autism and epilepsy, then he proposed this model in which, so the idea, sorry, it's a bit difficult not pointing, but so in the immature brain, if you look at the cell have been represented there, this cell is full of chloride ions, okay? And this is what happens in a newborn human or newborn mice. You will find neurons like that. And because they're filled up with chloride, they don't behave as a normal neuron. And so they filled up with chloride because this transporter, the NKCC1, so it's a sodium-potassium transporter, imports a chloride in the cell. And this is the one that is highly expressed at this stage. And then when the GABAergic receptor opens, you see that the chloride, instead of going in, goes out. And when it goes out, then GABAergic receptor behaves as an excitatory receptor, or maybe it will, well, let's say it will favorize the excitability. In the mature brain, because the second transporter has started to be expressed, the KCC2 transporter, chloride is going out. If chloride goes out, it lets the possibility for the GABAergic receptor to let it come in each time you have an activation of the receptor. Then it behaves like an inhibitory receptor, as it is expected to be. And then you have a decrease in the excitability. So what was proposed by Becker is that in the autistic brain, there would be a defect. It could be either that there would be too much NKCC1, maybe not enough KCC2, but in a way there would be too much chloride in the cell. This was based on the paradoxical effects of benzodiazepines in people with autism, in some patients with autism. And then when it behaves like that, so these cells are too, the level of excitability is too high. So a way you could reduce this excitability would be to come in with bromide. And bromide ions, what they do, actually they substitute to chloride ions because they have the same size and the same electric properties. And when they substitute to chloride, the good thing is that they block the entry of chloride, and they come in the cell, and they're easily to go out. We don't know how they do that, but they probably diffuse out the cell. So what you see, the result is that you would have a decrease in the intracellular chloride concentration, and that would be favorable to a decrease in excitability. I will show you that it's probably not the only mechanism. It was a putative one. What we did in this study is that we studied the effect of bromide ions at different doses, different patterns of administration, 2 different bromide styles to make sure, and in 3 different genetic models. And we looked at essentially behavior, because the idea is that if you diagnose autism based on a behavioral evaluation, you have to do the same in mice. So we did as much as we could to have a good evaluation of primary and secondary symptoms in our different models. We used also transcriptomics, and we used in cellular pharmacology. I will show you a bit of that at the end of the talk. So first of all, we gave bromide salts. So this is sodium bromide in a chronic manner. The idea is that if you use the molecule in the clinics, you will probably give it chronically anyway. So we gave it a week before we started the behavioral evaluation. There are many tests over there. Don't be too worried. I won't show you all of them. The idea is to have as many tests as we can, to perform as much as we can. If you look at the first test here, it's social interaction. So basically, you put 2 mice in an open field. They should not know each other, so they're novel partners, so not same partners, congenials, because they are the same sex and same age, and they're under the same treatment. And they will explore each other, as you would expect from a mouse. And we measure many different parameters, but here I show you the number of nose contacts. So you see that a mouse with an autistic behavior will make less contacts. These are the ones, the blue ones are the knockouts. This is the mu opioid knockout mouse model, so not expressing the mu opioid receptor. So you see that they make less nose contacts, and when you give an increasing doses of bromide, sodium bromide, you have an increase in this parameter, and they recover, let's say at 250 milligrams per kilo. This is the optimal dose. And when you look at the duration of those contacts, which is even better because it's more robust in terms of the quality, you assess the quality of the contacts. It's not only a matter of making many nose contacts, it's also a matter of making long nose contacts, means that the animal is confident and is comfortable with the social contact. You see that over 125 milligrams per kilo, you have a very good restoration of this duration. And the funny thing is that a week after, again, this is missing some translation, a week after it's still there. So you have some carryover effect, which is interesting for clinical application. When you give bromide acutely, it often happens that in mouse studies, people give only 1 shot of a drug and look at the behavior. This is not exactly the way you would, you don't know how it will behave in the, it's not, the translation is not good. I mean, in the clinics, you would never give 1 shot of a drug. It's very unlikely. It's better to have a look at chronic effects. Actually, if you do that with bromide, there is no effect at all. So it doesn't do anything on social interaction, except that you have some increase in the number of nose contacts. But on other parameters, there's nothing. Poor contacts, you have many parameters that you can measure here. So you need some accumulation. Accumulation is known because bromide ions have been used as a treatment for epilepsy for a long time, and it was known. Clinicians knew that they had to wait for a while before they have some effects. Now this is the second test. In this test, as you've seen this morning, you put a mouse in a 3-chamber apparatus. And you give it the choice between interacting with a living mouse or interacting with an object. In our case, the object is a mouse toy. Okay, so it looks very similar to the other one, except that it's not living. And it's important because in this paradigm, you will see that here in the wild type mouse will prefer. It will make longer nose contacts with the mouse, the living mouse, and very shorter ones, let's say, with the object. If you look at the knockouts, they do quite the opposite. They make longer nose contacts with the object, with the fur toy. And when you give bromide, since the very low dose of 10 milligrams per kilo, you have a complete rescue of the behavior. The mice, they turn preferring the living mouse. So this translates into a complete reversal or rescue of the preference ratio. So we compared to Bumetanide because it was supposed to behave a bit similarly. It's supposed to do the same, actually. So it acts on chloride gradients, let's say. So we expected to see some similar effects, and it was at this time it was still under clinical trial. So we made the experiments, and we looked at the effects of Bumetanide. It's chronic Bumetanide, so it blocks the NKCC1 transporter. And you see that you have a slight effect of Bumetanide in the social interaction test. Actually, it increases the number of contacts, but it doesn't modify the duration of those contacts. And the funny thing is that in the 3-chamber test, you have clearly, when you give Bumetanide to these knockout mice, you have a progressive increase. This is dose-dependent in the duration of the nose contacts with the living partner, but you don't decrease the interest for the object. So in the end, you have a partial restoration of the preference ratio. So then we looked at other behaviors that are often associated with autism. The first one is important because it makes part of the diagnosis triad, which is motor, which are stereotypes, but not only motor, we also look at cognitive stereotypes. But in this case, we have spontaneous, when the animals feel a bit anxious, they tend to display some stereotypes like circling. And you see that if you give either bromide or Bumetanide, you completely suppress that. And then the last test is an anxiety test, is a conflict test. So you deprive the animals from food for about overnight, let's say. And then you look at the time the animals take to go and eat in the middle of the arena with a bright light in the middle. You see that in the mu knockouts, you have an increase in this latency to go and eat in the middle of the arena that is completely suppressed when you give the bromide. But that's also expected because bromide have been used as an anxiolytic treatment for long. You have no effect of Bumetanide. So Bumetanide in all our tests is only very effective in suppressing stereotypes. And it's funny because it's actually what has been found in clinical trials. So we looked at potassium bromide, it was just to check. So if you give another bromide salt, it does the same. The only difference is that you have to decrease the dose because potassium is toxic. So you have to be super careful. We decrease the dose and we end up with 145 milligrams per kilo. And it does the equivalent thing of 250 milligrams per kilo of sodium bromide. So it's more efficient, but it's more delicate to use. And it works in all different aspects of the behavior. We also checked on two more models. The idea was to make sure that it's not only due to the model. Okay? So the two models we used, the first one is the model for Fragile X syndrome, FM1 knockouts. You have a complete relief of social deficit in the social interaction test to suppress motor stereotypes, and you also decrease anxiety. And in the Chang-3, so the Chang-3 model is a partial knockout where you remove the exons from exon 13 to exon 16, and you have a very severe phenotype. And when you give the bromide again, you are able to suppress all these defects. So you restore social interaction, suppress motor stereotypes, and have an anxiolytic effect. So what does it do, actually? What does the bromide do? How does it work? To have an idea about that, what we did is that we looked at transcriptomics. We looked at gene expression in different brain regions. And we focused on brain regions involved in what we would call the social brain and the reward system, more or less, actually. And we looked at different categories of genes on chloride transporters. You see that they are... So what you see globally is that under bromide, you hear in the knockouts, you hear is the knockout without bromide. It's not like bromide was normalizing gene expression. It doesn't do that at all. It does something on top. So what it does, it actually upregulates the expression of many different genes. So among these genes, you have the chloride transporters. So this is nice because these transporters are the ones that take take the chloride out, like KCC4, for example. You also have an increase in the expression of the subunits of the GABA-A receptors, like the alpha-2 subunit. So that goes in the right direction, so decreasing the excitation. Something less expected, we had a look on the expression of our favorite receptor, which is the mGlu4 receptor. It's a glutamate receptor. You probably heard about the mGlu5. We focus more on the mGlu4. This one is target. There's several treatments that have been developed targeting mGlu4 to reduce tardive dyskinesias in Parkinson's disease. So it looks more like istradefilin, for example, which is an A2A antagonist. When you give bromide, you increase the expression of GRM4, coding for mGlu4 receptor. So you would expect that maybe the mGlu4 receptor works better. And we knew that in the mu knockout, when you facilitate the activity of the mGlu4 receptor, you have a recovery of the behavior. So it relieves autistic-like behavior. So what we did in that last experiment, behavioral experiment, is that we combined a liminal dose of bromide, 70 milligrams per kilo, and a liminal dose of the facilitator of mGlu4 activity. In this case, we used the V0155041. And the idea was to look at the potential synergy between the two molecules. And that's what happened. When you give the combo in the social interaction test, you look at the turquoise bar, and you see that you have a complete recovery of the number, the duration here of the nose contacts, what you don't have when you give the treatments independently. What is really interesting is that this persists over time, after a week or after 2 weeks. So you have a carryover effect that is super specific to the combination of the two compounds. So this is highly promising. There is a reason for that. The reason that what was more or less known before, because our collaborators in Montpellier had shown that the mGlu4 receptor the activity of the mGlu4 receptor is dependent on the concentration of chloride ions. So the more you have chloride in the extracellular medium, the more the receptor responds. So you increase chloride concentration, you go to darker green, and you have this the big sigmoid. And actually, I will go shortly on that one, but if you look at the top, so this is pharmacology in cellulo. If you look at the conditions when you have, so you start with a basal level of chloride, like in a cell, it's 100 millimolar chloride. And you add something on top, either gluconate, which is an ion that is an artificial ion. It doesn't do anything in a cell, it doesn't go through transporters or anything. Or you add 50 millimolars of chloride, and then you end up with 150 millimolars of chloride. This is the green curve. Or you have the purple condition, you replace chloride with bromide. And what you see on the mGlu4 activity is that when you have the orange curve, so you need a lot of glutamate to activate the receptor, and you don't go very high. When you add more chloride, you start activating your receptor earlier, so at lower doses, and you go higher. And when you give the bromide, it's even better. So you start even earlier and you go even higher. So what it means is that you activate your receptor even more efficiently in presence of bromide. And these concentrations, they are physiologically relevant. So that's what you would expect to see in the brain when you give the doses we gave to the mice. And the scheme here in presence of the VU0155041, so this mGlu4 PAM, you have an additional effect. So if you put together the VU and the bromide, you have a big synergy. This is the purple bar you have at the end. So you have maybe not synergy, or an additional effect of the two. So actually you have a synergy. It seems that there is a synergy of activity between bromide and mGlu4 receptors. So what we could say, this would be the final message on the mechanism of this bromide treatment, is that it does two kinds of things. On one side, it seems that by acting on the expression of these different actors, so these are chloride extruders, either this was KCC4, for example, or the CSCA1, they work together to put the chloride outside the cell. And once you have less chloride in the cell, it's useful because then you can activate other actors of the signaling. And all these different actors, the NKCC, for example, NKCC transporters, the ABA receptor and NGLU4 receptors, they all work to decrease the excitability of the cells. But so you have first to put the chloride out, and then once the chloride is out, you can activate all these mechanisms. And on top of that, when you have bromide, bromide can substitute to chloride and do that even better. So which makes sort of an additional mechanism. So these together, they all work decreasing neuronal activity. So the conclusion of this talk is that actually we have beneficial effects of bromide, and they necessitate chronic administration. So this is nice because it matches with clinical use. We have validated it on in three different models, and this is good for it has a good translational value, at least better than if we had tested on only a single model, let's say. What is nice also is that we were able to predict that actually Bumetanide would not do the trick because it only relieves stereotypic behavior, and it's not so convincing in relieving social deficits. We know toxicity and pharmacokinetics of bromide salts since many years. They've been used for a while. We know that the bioavailability of these compounds is very good. So bromide ions, they're highly soluble and brain penetrant. They eliminate slowly, which can be an advantage and an inconvenience, depending on what you want. They are toxic. That's the problem. That's very well known. So you have a very narrow window of therapeutic effects, and you have to monitor bromide levels in the blood regularly. So you have to calculate the benefit ratio the benefit-risk ratio. So it depends on how severe is the autism before you can give this kind of treatment. And a way to go around that would be to combine with other treatments, like we did with the NGLU4 PAM, because and actually there is one that is available that's been approved in phase 1. It's the Foliglurax from Lundbeck Laboratories. So but that's a bit longer term because you need to go through more tests. So for now, I'd like to thank all the people who contributed to this work, people in our group, people at INRAE, Deborah, who worked on the behavioral characterization, and our collaborators at IGF, Julie Kniazeff and Jean-Philippe Pain, for having welcomed Cécile during her last PhD year. And finally, Thierry Plouvier, who was the guy who actually inspired this work, who came once and told us you should try bromide in mice because it will probably work. We didn't believe it at the beginning. And the paper is not out yet because it was just accepted in neuropsychopharmacology, but you can have a look at it on bioRxiv. Thank you very much.
Okay, thank you very much, Julie. Merci beaucoup, Julie. Des questions dans la salle?
Je suis prête à répondre en français, pas de souci.
Merci beaucoup. C'est une longue histoire.
Oui, très longue. C'est toujours long, de toute façon.
Non, moi, je suis très heureuse de vous retrouver ici. Bon, il y a deux questions. La première, c'est que c'est sûr qu'on voit bien qu'il y a une action qui est différentielle sur les différentes dimensions. Mais pourquoi pas? Mais moi, je vais parler d'un troisième point, c'est celui de la comorbidité avec l'épilepsie.
Oui.
Voilà, est-ce que
oui,
vous avez...
alors, on n'a pas testé, on a 3 modèles qui sont tous sensibles aux crises d'épilepsie. Donc, on aurait pu, par exemple, tester pour voir si leur seuil épileptogène était réduit sous bromure, ce qu'on peut s'attendre à voir, puisque ça a été assez bien testé, aussi bien dans le domaine préclinique, et puis c'est très connu en clinique. C'est toujours utilisé en médecine vétérinaire, les ions bromure. C'est pas très plaisant à faire chez la souris, j'avoue qu'on s'est lâchement défilé. Donc on ne l'a pas fait. Après, ce qui est intéressant, c'est que déjà basé sur les données de la littérature qui sont très solides, on pourrait imaginer adresser ce traitement plus particulièrement à des patients qui ont la comorbidité, parce que ça peut permettre de gérer les deux difficultés en même temps. On a aussi des données très intéressantes dans le syndrome de Rett, donc c'est à suivre. Voilà. Et avec un effet sur une autre dimension encore, je ne peux pas trop en parler, parce que on est obligé de breveter. Alors, c'est la logique. Je n'ai pas remercié nos partenaires là-dedans. C'est vrai que je suis un peu fatiguée, excusez-moi. Il y a Cevalo et Inserm Transfer qui nous ont beaucoup aidés et soutenus dans ce projet. Et donc, leur souhait, c'est qu'on brevette parce que ce qu'ils veulent, c'est que ce soit repris derrière et qu'il y ait vraiment un appui et des compagnies pharmaceutiques qui soient intéressées pour pousser ce traitement. Et avec Frédéric, on espère qu'on pourra pousser pour un essai clinique assez rapidement aussi.
Oui, merci beaucoup. C'était super intéressant, bravo. Quand vous avez parlé de modèles animaux, de modèles génétiques, modèles environnementaux, du coup, moi, ça m'a fait penser à d'autres études qui sont menées au sein du réseau. Et vous parlez de troubles occurrents. Je me demandais si vous aviez testé l'impact sur la dextérité motrice des animaux, ou si c'est pareil, c'est encore confidentiel.
Je pense que Jérôme, non. Ouais, c'est ça, c'est compliqué.
Okay.
Ouais, c'est une bonne piste. Voilà, c'est tout ce que je dirais pour aujourd'hui. Oui,
merci.
Il y a des choses qui se passent.
Très bien, merci beaucoup.
Je vous en prie.